today's lesson, we will be looking at distributed loads. Let's look at the learning outcomes for this lesson. First, find out where the resultant force is on an object and figure out where the resultant force will be located on the object. Many loading types are distributed loads, such as wind, hydrostatic, soil pressures, and live loads. The effects of distributed loads can be simplified by replacing them with the resultants. For example, in this diagram, all those little arrows can be replaced by a singular large arrow. The load intensity, W of x, is the force per unit length. The magnitude of the resultant force, R, this is equal to the area enclosed by the distributed load curve, which is equal to the integral of W of x dx, which is just the area under W of x. The location of the resultant force. The resultant R is applied through the centroid G of the area by the distributed load curve. Let's look at some common cases. First, we have uniformly distributed loads, such as this one. The resultant force will be equal to the weight multiplied by the length of the rectangle. This is also the area of the rectangle. It will also be located at the centroid of the rectangle, which is at L over 2. We also have triangularly distributed loads, such as this one. R will be equal to the weight multiplied by L divided by 2, which is the area of the triangle. It will be located at the centroid of the triangle, which is at L over 3. We also have linearly varying loads, such as this one. For these, we want to divide them into common shapes, such as rectangles and triangles. This one, we will divide it into a rectangle and a triangle, where the rectangle is W1 and the triangle is W2 minus W1. The rectangle's resultant will be located at L over 2, and the triangle's resultant will be located at L over 3 from the highest peak. Let's try out this example. We are given two lengths, A and B, where A is 1.2 meters and B is 2.5 meters. For this problem, we need to find the resultant of each shape as well as where they are located to find the moment. Let's start with the triangle first. We know that the resultant is equal to the area of the triangle, which gives us a force of 7.5 kilonewtons. To find where it is located, we know that it is at the centroid of the triangle, or B over 3 from the highest peak. Calculating this gives us 0.83 meters, and subtracting it from the full length of 4 meters, we get that it is at 3.17 meters away from A. Now for the rectangle. To find the resultant, we will once again use the area, which gives us 7.4 kilonewtons. It is located at the centroid, or A plus B over 2. Calculating this gives us 1.85 meters, and subtracting it from the full length of 4 meters, we get that it is located at 2.15 meters away from A. Now we can find the moment at A. First, we need to establish our positive axes. The resultant force of the rectangle is giving a counterclockwise motion, making it a positive moment. For the resultant force of the triangle, it is making a clockwise rotation, giving us a negative moment. Adding these up, we get a total moment of 7.87 kilonewtons meters clockwise. Let's summarize this problem. First, we found the resultant force as well as where it's located for the triangle, and then we found the resultant force as well as where it's located for the rectangle. Using this, we can then find the moment at A.